Welcome. We've looks like we've really only got one guy logged in. Well, two guys logged in remotely. And anyway, welcome everyone. Just for what it's worth, everyone's gotten the mistaken idea that Bud knows something about antennas.
Okay, well, I'll see you next week, everybody.
Let me put the record straight. Bud thinks he knows something about antennas, and there's a bit of a difference there. But the object here is to find a way to have a working antenna system in an HOA. And I might suggest that the best way to do that is don't buy a house in an HOA. Yeah. Problem is you can't hardly buy one anymore that's not in an HOA. Fortunately, I'm in one of those areas that's not. But there are the covenants in my neighborhood that renewed for another 30 years that prohibit telecommunications antennas. The problem with that covenant is that the city of Arlington some 25 years ago defined in ordinance what is a telecommunications antenna system, and then in the very next paragraph exempted licensed federally licensed amateur radio stations from that. So my response to the guys that are that would complain, sorry, Charlie. So I yeah. Nevertheless, for what it's worth, I have some hidden antennas in the trees, and if you've got trees, the world is your oyster. Seriously, we can hide an awful lot within the trees. Anyway, I want to get started with a few things, but Bud likes to be silly, and Bud likes to define physical laws. In fact, I used to do this in one of my previous lives where I was out doing lunch and learns with the professional engineering firms. I was selling thermally driven chilled water equipment, and I created a law that I would use just to lighten the mood a little bit, but also it made an important point in this equipment, and it was based on Kirchhoff's current law. But essentially, Bud's thermal law of gazins and gazouts says for every gazin there has to be a gazout. Otherwise, this equipment's not going to work. It's going to reach some equilibrium, and that's going to be it. Well, so we're going to have a little of that kind of silliness today, because we're going to start. Well, okay, so we're going to start with Bud's first law of antennas, and that starts out with there being only 30 billion trillion perfect isotropic radiators in the observable universe. That's a 30 followed by 21 zeros. According to NASA, there are more stars in the observable universe than there are grains of sand on this planet. Is that amazing or what? All right, so with only 30 billion trillion perfect isotropic radiators, all the rest of them, therefore, must be a compromise. Hence, if it's an antenna, it's a compromise. Well, that's Bud's first law of antennas. What about the second one? The radiation efficiency of any antenna system is directly proportional to the physical length of the radiating element up to a quarter wave. I've seen a lot of antennas that seem to be very well designed, but the radiating element on them is so short that they're useless. One of them is Yaesu's ATX20. What's that thing called? AT120. I figured out the reason why the radiating element's so short is so they can do 2 meter and 70 centimeter. Why in the world would you want to have a single antenna do all of that? Makes no sense. Anyway, of all the antennas that I've had to deal with, that one is the very worst one I've seen anywhere, anytime. And it's because the radiating element is just too bloody short. Anybody wants to see the one on my car later, I've got, and I've got some photographs as we go on, but I've got a mediocre loading coil on it from Wolf River, and a 108-inch whip. Now, there's two reasons I have a 108-inch whip instead of a 102-inch whip. One, I could buy it. MFJ had them on sale to get rid of them. That's the length that you would use for a CB radio. And the other real reason is because it's 6 inches longer than a 102-inch whip.
Well, what about fitting in your garage?
No,
Having to take it off.
won't fit in the garage.
Okay.
All right.
Won't fit anywhere because I got a great big one mounted on my van.
Bud's third law of antennas. Reactive power does not radiate. It circulates. So if antenna efficiency is basically the ratio of radiated power divided by the transmitter output power, then a reactive antenna system will have a lower efficiency than a truly resonant system. Now, you've probably read on QST somebody, even with an extra class license, making a statement that, well, a random length wire will radiate just as well as a resonant wire. And I'm here to tell you that's bullshit smothered in onion gravy. It will radiate any real current that is on that wire. The problem is it's going to have to deal with a pretty significant power factor. The most critical part of this is to be resonant at the radiating element. It doesn't do you any good to be non-resonant at the radiating element and everything else appears resonant, because you're still going to have the problem with reactive power. The higher the power your antenna will support, the higher the antenna efficiency. In a nutshell, that's simply because there will be fewer losses in both the magnetics, the ferrite cores, and in the wires, the conductors. Remember that the higher the frequency gets, the higher the resistance becomes in any conductor due to skin effect. So you may measure through the whole system a half ohm total resistance, but that's at DC. It could be several hundred ohms or more at 30 megahertz. All right, let's see if I can figure out how to work this thing. Okay, now the next little part of this is a teaser for Smith charts. If anybody later is interested in going over Smith charts again, the last time I did one, I did a 1 hour shorty on Smith charts at Hamfest. We can do that again, but I don't think this year I'll be available to do it because I'll be out taking tickets. But we'll do another presentation or series of presentations on Smith charts if anybody wants to deal with it. But because reactive power is such a problem, I wanted to leave this teaser and let everybody see a little bit what it is. So there's really two types of reactance. There's capacitive and inductive reactance. And essentially what a reactance does is it introduces a phase shift between the voltage and the current. Now, this is a real problem for the electric company. Anytime you've got an inductive device like the motor on your air conditioner, it's going to cause a lag in the current versus the voltage. And so then they have to supply more current to get the power that's required for that motor. So it increases their losses. A lot of the larger commercial users their power factor is measured and they're dinged for it. On an inductive, you get what we call a positive phase shift where the current actually lags the voltage. On a capacitive, it's the other way around where current leads the voltage. I'm sorry, current leads and voltage lags. Inductive reactance is calculated. It's represented as X sub L. It's calculated as 2 pi times the frequency times the inductance in henries. Capacitive reactance is the reciprocal of 2 pi times the frequency times the capacitance in farads. And it's represented in ohms. The resonant frequency is where the reactance for the inductance and the capacitance are the same, canceling each other out. Note that the inductance is positive, the capacitance is negative. If they're equal, let's say they're both 3 ohms, plus 3 minus 3 equals 0. And now the circuit is basically resistive. All right.
Go back to that last slide.
We'll post these.
Okay, great.
All right. All right. Any number multiplied by itself is said to be the square root of the product. I have this 5-year-old grandchild that likes to be drilled, and he learned a lot of math. And I'm messing with him. Weston, what's the square root of 81? 9. What's the square root of 9? 3. What's the square root of 9 times the square root of 2? 6. Well, Weston, what's the square root of 1? It's 1. This is a 5-year-old. He learned all this on TV.
Wow.
I stumped him. What's the square root of minus 1? Gotcha. His mama, who's a pretty good mathematician, had to explain him, and she did. But it's an imaginary number. It doesn't exist. But it works in math. If I take the square root of minus 1 times the square root of minus 1, what do I get? Minus 1. The square root of minus 1 times the square root of minus 1 equals minus 1. Okay, so the mathematicians define that as operator I for imaginary. It's an imaginary number for whom the math works. But since the real engineers, the electronics and electrical engineers already had a definition for little I, that's AC current, we decided to call it operator J. So you'll see this an awful lot of the time. So you'll see a complex impedance described. In this case, an example is 37 plus J 12 ohms. So that would be 37 real or resistive plus 12 reactive.
So does it still end up being, with that, still end up being 49 ohms that you would consider your?
No, in this case, it's 39 ohms.
Okay.
At an angle of 18 degrees.
Okay, so you still have to operate on to figure out what it is.
Right, and I'll show you how to do that. Okay, so that formula is a complex formula. It's complex math, but in this case, really it's two-dimensional complex math, and it's called a phasor. In the terminology, resistance is real. Reactance is imaginary. Resistance is shown as an R. Reactance is shown as an X. If you look at your antenna analyzer, you'll probably see that it's got R equals some number, X equals some number. How would I know if it's resonant at that point? X is 0, right? Impedance is the complex phasor, and it's represented by Z as in zebra. Real or applied power, this is the power that does the work. The older guys are going to call it real power. The newer graduates are going to call it applied power. Same thing. It's the one that does the work. In our world, particularly when it comes to antennas, what is the work that's being done? Radiating. Bingo. Reactive power, called VAR, or volts amps reactive, is a result of those reactive components. And apparent power is a combination of real and reactive power. Have you ever taken your radio that it says it's 100 watts, you set it for 100 watts, and you're keying up, and you notice that it's actually, your external power meter shows that it's actually putting out 110 watts? Have you ever wondered about that? That's because that meter's measuring apparent power. It's actually saying, okay, I've got so many volts across a certain impedance. Therefore, I have so many E times I, or E squared over R equals power, right? That's what it is. Very few of the real power meters out there are measuring real power. If it's a bird watt meter, it's measuring real power. Okay, the Pythagorean theorem applies on this thing. Notice that I've got a right triangle here with an A, B, and a C. A squared plus B squared equals C squared, or C equals the square root of A squared plus B squared. All right, A represents the reactive or imaginary parts, the vertical axis. B equals the real or resistive part, it's the horizontal axis. C, the hypotenuse, equals the impedance or the complex. So see the equation for Z? That's also the equation for real power, or for apparent power. Now, this is a couple of formulas that you really should know if you don't already have your extra class exam. There are questions on there you need to be able to convert between polar and rectangular displays of phasors. Theta, this angle theta up there, is the arctangent of the reactive divided by the resistive, or the reactive divided by the real. And then the real equals the apparent power, or the impedance, times the cosine of theta. And the reactive equals the hypotenuse times the sine of theta. And that way you can do a polar to rectangular conversion, or rectangular back to polar conversion at your will. So here are two formulas that represent the same phasor, the same complex number. In this, and I just pulled these out of the air. Impedance Z equals, in parentheses, 5 on the real side plus J 4 on the imaginary side, which is also equal to 6.4 at an angle of 39 degrees. Now, what you really want ideally on here is resonance, which would give you 5 plus J0. Or in our case, we want 50 plus J0, somewhere between 50 and 78. All right, now how do I represent that graphically? Notice that it's 5 plus J4, so 5 on the horizontal, so go to the right, 5 notches on the horizontal, and then 4 on the vertical. It's positive 4, so you go up 4, and that gives you, that point is Z. Notice that the hypotenuse is longer than either of those two lines. All right? How did I get that? Pythagoras Theorem. So it equals, so the magnitude of the impedance here is 6.4 ohms, but it's phase shifted 39 degrees. All right, power factor. It reflects the effect of having the current and voltage in a circuit that's out of phase. It's the ratio of real power to apparent power. How much is on the horizontal axis versus what's on the hypotenuse, the magnitude of the hypotenuse. Power factor is always determined by the load, not by the generator. And the most critical load point that you've got to deal with is going to be the radiating element. And that's why I argue vociferously against the idea that a random length wire will radiate just as well. Only because it's going to be so reactive that much of the radiating power is going to be lost. Now, technically, it's radiating as much of the real power as you're putting on it. It's just that it's reducing the amount of real power that's available at that point. All right, a power factor of unity means that 100% of the power in the system is real power. At resonance, capacitive reactance and inductive reactance are equal, effectively canceling each other out. This makes the load purely resistive. At resonance, power factor is virtually unity. At resonance, the voltage across the element equals applied voltage times the circuit Q. Now watch this one. If I've got a coil with a Q or a quality factor of 200, and I apply 10 volts AC to that, then the voltage dropped across that inductor is going to be 2,000 volts. Think about that. The higher the Q, the narrower the bandwidth. So that means that the lower the Q, the wider the section of the band I'll be able to support with an SWR that stays fairly low. The higher the Q, the more I'm going to have to change the tuning on that. The other side of that is the higher the Q, the greater the efficiency of the radiator. That's important. That's very important. The lowest SWR is rarely at the point of resonance. And that's very simply because SWR doesn't have anything to do with resonance. It has to do with impedance match. Anytime there's a difference in impedance, in the magnitude of the impedance between a feed point and a load, you're going to have a reflection. That's how a stealth aircraft works. The impedance of free space is 377 ohms. The impedance of that aircraft is something different than 377 ohms. So when there's a difference there, it causes a reflection. That's how radar works. But if I can make that aircraft 377 ohms, guess what? No, it's invisible. There's no reflection. The same is true in our case. If I can make the feed point on my antenna the same impedance as the transmission line that plugs into it, no reflection. That's what I want, ideally. Okay, simplest little explanation that I can give now. The foam up there is just kind of useless, right? Well, okay, you can look at it, you can blow it off. It actually represents, in this illustration, the reactive power. The liquid beer underneath it is the part that gets you drunk. That's the work in this. It's getting you drunk, right? The combination of the two is the apparent power. Remember, the power meter in your radio and the power meter that you've probably got on your coax out there are apparent power meters, not real power meters. If you really want to know how much the real power is, get a bird watt meter. Okay, now let's talk about a few inconvenient facts. Most modern transmitters will start to reduce power output from 100 watts peak envelope power as the SWR increases above 2 to 1 to protect the transmitter finals. Does everyone understand why that is? Anyone that wants to know later, I'll draw you a picture and make it like a story, and I'll explain to you why that is, because it's really quite simple. Antenna tuners do not solve the problem. They only mask it, so the transceiver does not reduce power out. They do not necessarily help. Depends on the situation you're in. Horizontally polarized antennas close to the ground tend to be reactive. Vertically polarized antennas are more susceptible to noise in an urban environment because an awful lot of that noise is vertically polarized. For the lower frequencies, the vertically polarized antennas will tend to have a lower radiation efficiency due to the length of the radiating element. Often a direct earth connection helps. The lower the frequency, the longer the radiating element wants to be. That can be a problem when you're trying to hide your antenna. Any vertical antenna less than a quarter wave long will require direct connection to ground with radials and a loading coil. That's not actually quite accurate. Many vertical antennas less than a quarter wave long will really want a direct connection to ground with radials and a loading coil. There's a lot of disagreement on how important that is. It seems to be you're going to have radials for a vertical of some form. And connection to ground is very helpful on the very far field. the distant far field. The speed of light in an antenna's radiating element will vary based on its distance above ground and wavelengths. That means an antenna that's 30 feet high is one distance above ground at 20 meters and a different distance above ground at 40 meters. That makes it hard to do multiband antennas with a single wire. How about some convenient facts? Center-fed dipoles will go resonant on the fundamental and all odd multiples of the fundamental. So, any 40-meter dipole, if it's tuned to where the best ASWR is down right around 7 megahertz, will also work on the 15-meter band. Off-center-fed dipoles will go resonant on the fundamental and all even multiples. So a 40-meter off-center-fed dipole should do 40 meters, 20 meters, and 10 meters on the one wire. An 80-meter off-center-fed dipole will do a whole lot more than that. Infed half-wave dipoles are actually an off-center-fed that is fed all the way over at the end, and they'll go resonant on the fundamental and all multiples. Now, I want to pass this one around because there's a couple things I want to point out here. Notice, first of all, Bud has a rule when it comes to buying antennas. I bought several of these, but I'm not going to do it ever again. Never buy an antenna that's packaged that has the end terminated where you can't unterminate it and adjust the length of the antenna. You just wasted your money. I don't care how much you pay for that antenna. It may or may not work where you put it. They probably tested it with their balun at 25 feet above the ground over their ground. Now put it at your house and see what it does. So I want to pass this around, let everybody see this. This is, and feel free to unwind it. This is one of the ones that we did as a build-a-thon last year, and it works fairly well. I'll tell you a couple of things that I did different than most of the guys. We wanted this to be portable, so they came with QRP power capability. I said, no, I'm not doing that. It has to support at least 100 watts. That one does. And the other thing was it had real thin wire. I said, no, that's too many losses. Okay, I understand. It's in a backpack. I want to keep it small. I want to make it easy to put up in the tree. No, I've got heavier wire on there. Why? Efficiency. This one is not a particularly efficient antenna. But again, it's a compromise, right? Okay, now, convenient fact. 1 S unit represents about 6 dB. So going from 5 watts to 10 watts is an increase of only 3 dB. So that's a half an S unit by doubling my power. Going from 5 watts to 50 watts only represents about 1.5 S units at the receive end. The moral of this story is a half-wave antenna does not require, well, the moral of the story is that the antenna doesn't have to be perfect and highly efficient to be useful, because there's a lot of room for slop. And a half-wave antenna does not require ground or radials. Now, a random wire antenna always requires a ground to work against. But you already heard my opinion of random wire antennas. There are times when they're useful. Like, for instance, you're a Mars operator, and you got to operate on really screwball frequencies. Well, how you going to do that? You have to be able to move around in some, so it's going to be hard to get a multiband antenna. So a random wire with a tuner at the feed point is a useful item. All right, so now how do we go about developing an antenna system for our house in our HOA? First rule is define what you want to accomplish. I used to have this problem in the thermal chilled water business because I developed a process for solar air conditioning using hot water. My chiller, you put hot water in, it's got chilled water out. You make an air conditioner out of it. So you put solar panels up to generate the hot water, and you drive the chiller with it. The funny thing was, all these licensed professional engineers were flying by the seat of their frickin' pants, just saying, well, I'm going to put a bunch of panels up here, and I'm going to point them this way, and this seems like it's the right thing. But they never really went through a plan. And the truth is that only about 1 out of every 100 solar systems that were put out there actually work. I can tell you the process that I developed actually worked every time. But it started out with defining, what am I trying to get? So what do I want the antenna to do? Other than I want it to talk, but get more precise, all right? What's most important to me? And I'll show you what we did here with Anthony in a minute. What am I willing to compromise? What am I willing to trade off in order to get this thing? Step 2, plan your installation. All right, I need this balun. I need this much wire. I'm going to hang it at this location. In my house, I've got it hanging between some trees. At Anthony's house, we stapled it along the fence. So plan your installation. Then execute your plan. Order the parts, or go to Home Depot and pick up the wire, whatever you got to do. Then measure the result. You got to have an antenna analyzer to do that. Measure the result. Then adjust to the results where practical. Now, I'm going to show you one of this tool that we've got that you can use to do the planning, the design work, and do a 2-step adjustment to the results. So we needed to put up an antenna for Anthony, KG5 JPU. As y'all can tell, Anthony's blind. Well, he's legally blind. I mean, he's not completely blind. He can see some things. But you know, he's our friend, so we like to. He's blind as a bat. All right, and he's a good sport. But Anthony had an Infed half-wave antenna from it was an MFJ. We picked it up at HRO, but it failed in Texas weather because water got into the unit.
Is it a balun?
It's an unit.
Yeah, okay.
Not an Infed. Okay. So, defining what we need. Anthony's legally blind, but he has some very limited vision. He has a radio with a built-in antenna tuner capable of matching a system with a 3-to-1 SWR down to 1-to-1 at the push of a button. It's good. His radio does something else a little unusual that I'll tell you about. He probably doesn't even know this, but it doesn't matter. He lives in an HOA, and guess where the Nazi lives? Right across the street.
We used to.
Oh, you got rid of him, huh? Good.
Died.
Yeah. Well, yeah.
Our plan worked, fellas. All right.
He got tangled up in a high-Q coil when Anthony was radiating. Anthony desires the ability to work all of the HF bands. Now, just because he desires to work all of the HF bands doesn't mean he necessarily gets to. His radio will transmit at up to 100 watts peak envelope power, as long as the SWR is 2-to-1 or less at the radio. All changes must be made by the touch of a button, as he's blind. He can't go out there and make manual changes to this quickly and easily. He needs to be able to sit right in front of his radio. He changes band. He needs to push the tune button on that ICOM 7610.
7410.
7410?
7410.
Well, then I lied because I put it in 7610.
No, it's a 74.
Thank you for correcting
That's
me.
what I wanted, 7610.
Anyway, he has to be able to just push the button to do it. So we decided to do a multi-band antenna that was capable of resonance on almost all HF bands, not counting the wharf bands. It must present to the radio an SWR of 3.0 or less on all desired bands without the tuner. Now, in Anthony's case, well, for instance, with my Yaesu radios with the built-in tuner, if it won't tune it to 1-to-1, it takes the tuner out of the circuit. So it's either all or nothing. In Anthony's case, if it can tune it down below 2.0 to 1, it'll leave it in. So we can actually get away with a little higher SWR on Anthony's radio. Yes, sir.
I got a comment. The antenna before the current one that's up there, we had an issue, I think multiple issues. We might have calculated the length wrong because of the distance, and there were issues, especially after it rained, that it appeared in on-site that the water that was either in the ground or in the wood was affecting the antenna performance. And what was happening was I could be tuned and I'd be operating 100 watts, and then all of a sudden the SWR would be going up, or the mismatch, the visuals, and the radio was folding it on itself back. If that makes sense.
Yeah, actually it does. But I don't think we experience that problem anymore.
No,
okay.
But that's what we.
All right.
But I wanted to bring that up because that was another issue we were dealing with.
Yeah, back to number 2. It must present to the radio an SWR of 3.0 or less. You actually can get away with a little more than that well, from time to time. Ideally, though, it'll provide an SWR under 2 on all bands without the tuner. The antenna system must be capable of at least 100 watts PEP. The higher that figure is, the more efficient that antenna is going to be. It must be invisible from the street and especially from the Nazi's house. It must be able to provide both NIVIS, that's a near vertical incident skywave, and a low angle of radiation so he can talk anywhere he wants to talk. Now, we know that it'll give him good NIVIS because on 80 meters, I can talk to him from my house in Arlington to his house in Denbrook.
Works great.
It must be resilient in the face of Texas weather. We already had that problem. All right, so what did we do and how well did it work? Well, we put an 80-meter off-center fed dipole up. It's stapled to the top of his wooden fence at 8 foot above the ground for most of the distance. It makes a 90-degree turn at the back of the yard, then drops down to 6 feet above the ground. The entire length of the antenna is 126.14 feet, with about 30 inches after the 90, with about 30 feet after the 90-degree bend, and approximately 15 feet at 6 feet above the ground. This antenna is too close to the ground to work. And we have continuously counseled Anthony to stop making contacts all over the world. This week he made one in Bulgaria. He's made contacts in Japan, New Zealand, Australia, Austria, Italy, Canary Islands, Spain. You get the drift, all right? This antenna does not work. Would you please quit making contacts all over the world? Okay, so
and I was operating one time, and I didn't realize that I was operating on 50 watts when I first got the radio, and I didn't know. I thought I was operating at 100. Wow. And I actually hit Crooks Island, which is off the coast of New Zealand, operating at 50 watts on 15 meters.
On this piece of wire, stapled to can you see it? Now, this is from the front yard, where the 8-foot fence extends some out in front of the house. Can you see the wire?
Barely.
There's where it gets to the back. Can you see the wire? It gets to the back where it makes a 90-degree turn?
Very well.
Let's skip to that. Can you see the wire where the fence drops from 8 foot to 6 foot?
No, I can't.
We just came straight down and straight over. It's just stapled to this fence. And by the way, if you look closely, you can see the white stuff on the insulation. That wire probably needs the insulation replaced. It's indoor wire. That's what I recommend that you use, THHN wire. But UV screws it up over time. So we probably should replace it at some point. Also, some of the staples have come loose, so you see it sagging there a little bit.
The other thing is I realized when he told me the other day when he came by to look at my antenna and test it out and stuff, I didn't realize, because I thought it's been up there for 2 years. The last time we put
been
that
up there
antenna
for
up, it's been up
4
for 4 years plus, and it's still going strong.
Yeah. Okay. So here's the Ballon, and it's a current Ballon. This one was an inexpensive one. It was like $35. Dave Martin bought this as a kit from MFJ and assembled it.
And It's an off-center.
It's a 4-to-1 balun for an
Alright.
off-center fed dipole, yes. And now there's a much better balun out there from Balun Designs. I strongly recommend. Anthony wants to replace it. Ain't no way, it ain't broke. We don't fix it. This thing works too good.
Even the guy at Balun Design was telling me you're using the wrong balun. It shouldn't be working. You need to get this one and try this one. It's a hybrid balun and it'll work better.
Yeah, he doesn't need a hybrid balun, but it doesn't matter. I ain't changing it. It works too well. I'm sorry, it doesn't work. Stop making these
Right,
comments.
I know.
Okay, so here's his radio, and you see that little thing on top of the radio. That's that frequency display. That was something that one of our other members
No, it wasn't Mike. It was Mark.
Mark Kohlross did that just specifically for Anthony.
I can see.
All right, so here is the SWR on Anthony's radio, on Anthony's antenna.
That's before the tuner? With the tuner
There's no tuner engaged at all. That's the Rig Expert 650 connected right to the coax at the radio. So I disconnected it from the radio, plugged it straight into it. So yeah, there's no tuner involved here. Look at the 80 meter. That's really rare, but the 80 meter is almost all of the 80 meter band is without a tuner, 2-to-1 or under.
But I got a question to ask you when you're finished.
That dark blue line up there represents an SWR of 3-to-1. Can you see the 40 meter band there? Notice that it's above 3-to-1 most of the time, but he can still use it because of that fluke on that ICOM radio. So if he can get it below 2-to-1, it'll leave the tuner in place, so he transmits full power. Notice the 20 meter band, the whole thing's under 3-to-1. The 17 meter band, it's all under 2-to-1. The 15 meter band, same thing, it's a little over 3-to-1. The 12 meter band, which shouldn't be useful at all, is useful. And then of course the 10 meter band, the entire 10 meter band is useful.
Did you try 6? Because
Yes. I just didn't display it on here.
Right, and I do 60.
There are areas within the 6 meter band where it works. Now this is just an explosion of the 40 meter, and so you can see that about half of it is above 3-to-1. Nevertheless, he's able to operate on the 40 meter band.
And this is before you're hooking it up to the radio and using the internal tuner to tune it.
This is without the tuner.
Right, now
Okay.
here's the other question. Since we were outside, we noticed that I had a bird nest.
No, what he had was, all right. What he had was another ham came around to help him out with some stuff. This guy has a 2x2 call sign. That means he has what kind of license?
Advanced extra.
And he had his RG8X, there was excess, so he had it basically all tangled up, wrapped too tight, and tied with a piece of wire to a pole, and it had really screwed things up bad. But aside the fact, it probably ruined that coax. When we make another change, we'll probably replace all that coax on his thing. I wanted to bring that up. When the specifications for a piece of coax says you can only bend it so tight, pay attention to it. It's not a joke, but it made a huge negative difference on his antenna because of that.
And then after we untangled it and rolled it up nicely, and then we did all the testing, it made everything even more happier in range where it was.
Yes, it improved things dramatically. Now, okay, so we want to talk about some trade-offs, because one of the things that you got to decide is, what am I willing to sacrifice? What am I willing to compromise on? With an OCF dipole, a current balun is required. Most of the OCF dipoles that you can buy that are packaged, which I'm telling you not to buy anyway, because you can't adjust the length, use what's known as a voltage balun, because they're a little more tolerant of things that would interact with the antenna. The problem with that is that unless you've got an extremely good common mode current choke, then the coax becomes a part of the tuned antenna system. You change the coax, you just change the antenna. Not to mention the fact it screws up the radiation pattern. Now, in Anthony's case, the radiation, I'm going to run out of time, Anthony.
Yeah, go ahead.
Let me go through this.
Go ahead.
In Anthony's case, the radiation pattern is probably pretty screwy to start with. And anytime you're doing a long wire, like an OCF or an Infed halfwave, you're going to, the radiation pattern is going to get goofier and goofier as it goes up in higher and higher bands. So you need to have a current balun or something that's specifically designed to isolate the coax from the antenna. There are a limited number of bands available on a 40-meter OCF. You're going to find that in many of your cases in an HOA, you're going to need to, you don't have the real estate to go more than 40 meters. But with a 40-meter OCF, you get 40 meters, 20 meters, and 10 meters. That's it. With an 80-meter, you can get a lot more. But you should be able to get a minimum 80, not 75. In his case, he gets 75, but that's rare. You normally should be able to get 80, not 75. Then you would get 40, 20, 15, and 10. The good news is that you might, with a pretty reactive antenna, get 17 and 12. Which he gets, but it's highly reactive in that point. I'm going to run out of time, man.
I know. But the other thing I wanted to tell you, explain, when I had my initial off-center fed antenna that was put up, we had a choke put into the system. And we had it going before it went into the radio. And we realized that having the choke, and correct me if I'm wrong, but having the choke next to the radio made the feed line part of the antenna. Correct?
No, it did not.
It didn't.
It did not. It did not. And the only reason for putting a common mode choke at the input to the radio is you can get a lot of urban noise induced into the coax sheath, the shield of the coax, and that common mode choke at the radio will reduce that noise into your radio and improve your signal to noise ratio. All right, ground connection to an antenna is not required with an OCF dipole. If it's high enough, it'll likely require no tuner at all. For instance, at my house, except for 75 meters, I do not need a tuner for any of the bands except the 30-meter and 60-meter bands. It's very resilient in the Texas climate, particularly if you use the balun designs balance. It's relatively inexpensive. Spend about $100 on the balun. And then you buy this 12 or 14 gauge, same kind of wire on that Infed halfwave I passed around. 12 to 14 gauge works very well from an efficiency standpoint. And you can buy that at the big box hardware stores. I recommend one of these three baluns from Balun Designs. And again, we'll post this presentation online so you can grab this anytime you want to get it.
Now the guy from Balun Design. Okay.
We're out of time.
Okay.
I'm going to run out of time. I've only got an hour here, so please, sorry. This is actually this Infed halfwave is actually a form of an OCF dipole. It's just that the feed point is all the way off center. It requires a 9-to-1 or greater unin to work. 49-to-1 is available now, and the higher the number, the better. The reason for that is at the end of the antenna, at the end, current is minimum, voltage is maximum. The impedance is the voltage divided by the current, right? Current is almost nothing. Voltage is very high. That's like dividing by 0, you get infinity. So the impedance at the feed point of an Infed halfwave antenna is nearly infinite. It goes resonant on the fundamental and all harmonics. So a 40 meter will do 40, 20, 15, 10, and 6. It can be configured as a slanted, a flat, or an inverted V. You can feed it at the end, hang it over a tree in the midpoint as a V, and it'll work just fine as an inverted V antenna. If you use black wire, it's practically invisible. Now, I keep 2 antennas up in my trees at my house using black wire, and if you didn't know they were there, you couldn't see them. You'd have to know they were there to go looking for them. All right, here's one way that you can configure this. I've got my house over here with a chimney, so I've got the open end hooked to the chimney. The unend is tied to the fence, and I've got some angle there. The negative on this is that it's somewhat directive when you do that. It's directive towards the direction that it slants. You could, instead of the chimney, do it as a tree. This next one is one that I did. It's one of these. We tied the feed point to the fence, and the other end we hung up in a tree in the backyard. Look at that sucker. The dark line is at about 1.5 to 1. That's a pretty good antenna. Now, notice one other thing, and we'll get to this at the end, but notice where the lowest SWR is on the 40-meter band, and then look at where it is on the 20-meter band. And then look where it is on the 15-meter and on the 10-meter band. The reason for that is because the speed of light varies based on its height above ground in wavelengths. So we really need to find a way to compromise. If I tune this thing for 7 megahertz, I wouldn't get those other bands very well at all, if at all. Okay? So in the tool that I'll show you later at the end, there's a little bit of functionality in there to give you a way to compromise this a little bit and get as many of the bands as you can. Trade-offs. Well, they're similar to the off-center fed antennas from a trade-off standpoint. They work best when they're deployed as slanted or inverted V. It requires a longer feed line to get to the feed point. Now, I did do one of these where he put the feed point up at the chimney, and that gave him a lower SWR, and then the other end we tied off in the far corner of his fence right over the swimming pool. Worked pretty well. It's a very good solution for limited real estate with a 40-meter fundamental. I strongly recommend this as something that you consider. How about we have something that's temporary? So in the case of a temporary antenna, okay, I don't want the neighbor to see my antenna. It's in the garage. All right, I'm going to get out and do a little work this afternoon or this evening. I'll carry the antenna out into the backyard and hook it up. When I'm done, take the antenna down, put it back in the box. Buddy pole will work fine for that. Now, of all the ones that I'm going to show you today, this is going to be the poorest performer. Can anybody guess the reason why?
Short link.
Bingo. The combination of the two. Okay, so it's a horizontally polarized dipole. That means it's not terribly susceptible to urban noise. It's broadband, so it'll cover everything from 7 megahertz to 54 megahertz. It's easy to set up and take down, and it's available as a complete system in a bag. It's also relatively reasonable priced for what you get, but just bear in mind, I have never made a contact with someone on a buddy pole that I considered a strong signal. I suppose if he was right next door, it probably would peg my S meter, but usually they're down in the noise. It is not an efficient antenna. It's probably reactive, highly reactive due to close proximity to the ground, and that's really affecting the efficiency. This is the one, the portable, that I am the most impressed with today.
Awesome.
Our CW team deployed one of these during field day.
I've got the spec sheet and I can send it in.
Well, and we've got a, you can build this yourself. This thing, now it's got some trade-offs. So all you have to do is know what are the trade-offs, because what did I do? I planned on what I'm willing to compromise on, right? But essentially, this is an elevated vertical quarter wave antenna from 20 meters up through 6 meters with a telescoping whip.
40 meters with a coil.
Well, we'll get to that.
Okay.
All right. But it's you tune it by adjusting the length of the whip. Well, guess what? I hadn't got any crap in there eating up my power. And I can tune this thing to resonance real easy. This is a beautiful idea. The other thing is a vertical antenna needs a ground plane. So what this guy did was he created a segmented radial set, 2 radials. So I can set them out this way, which you give me somewhat omnidirectional. And this is not ideal, but it works. It works plenty well enough. I'm telling you that our CW guys made a ton of contacts on this. If I put it at a 90 degree like this, then it becomes somewhat directional in the direction of the center of that V. You can create these segments, and he provides you in the instructions how long they need to be up through 20 meters. If you're going to do more than 20 meters, you're going to need to have more segments. I'm thinking that Anderson power poles would be an ideal thing to interconnect these segments with. Now, there are a couple of trade-offs here. One of them is it requires the radials to be elevated. Now, because it requires radials to be elevated, I think it's very unlikely that connecting earth ground to the radials is going to help any. I don't know that. One way to find out, try it and see if things improve. Trade-offs. It works very well at 20 meters and up. It's easy to tune and can be expanded to 40 meters and 80, 75 meters, or anything from 3.5 megahertz to 30 megahertz. There isn't any reason in the world that you can't do Mars with this antenna. I can't say enough good things about this. I am so thoroughly impressed because it's so easy and it's cheap.
What is it called again?
It's called the Poda Performer. Elevated vertical antenna.
It's a retired Silicon Valley engineer that lives in the San Francisco Bay Area, and he just enjoys building antennas on the side just for fun. And he designed this one and posted the specs. Sam and I each have one. Built one.
K6ER.
KJ6ER.
Is this the one that you can either build yourself or you can buy it?
I don't think you can buy it.
No, you can build it, but this would make a great project for Build-a-thon Pro. I'm telling you. And he gives you he gives you everything you need, parts list,
Amazon,
the whole works.
I mean, you just go down the list and click on it. The only thing you can't order from Amazon is the Chameleon 7.
Right. Now let's talk about some negatives. It bottoms out at 20 megahertz or at 20 meters. So if you're going to go a lower frequency, you're going to have a loading coil. The one that the guys used at field day was a Wolf River coil. Wolf River loading coils are fairly functional. They're mediocre at best. I think I measured the Q on mine at about 60. If I really wanted a good one, they would have a Q in excess of 200. You want a Q in excess of 200? Texas bug catcher. But they cost more, okay? What are you willing to compromise on? The negative is it requires manual intervention to change the frequency. So you can tune this thing with the length for the 20 meter and above bands and mark it off and say, okay, I know this is where I need to be for all the way up for 20 meters and below, but say 10 meters, it's so many of these not extended. And Sam's done that with his.
Once it's tuned, will it cover the entire band, or is it frequency specific.
I only tested it on one band, but it covered the entire band. I think it was a 20-meter band that we tested it on.
When I tune it, at least for me, it'll cover the whole band. At so I don't need to readjust if I want to operate at a certain part of it.
So the Q's not real high, but again, the Q doesn't need to be real high because there's no loading coil. Now, when I throw a low Q like a Wolf River loading coil into it, well, it is what it is. But do I want to use 40 meters and 80 meters? Well, duh. So someone will get my Wolf River coil out there. But it's manual intervention every time you want to change bands. Is that a bad thing? He can't do it, but I can. It's susceptible to more urban noise. Why? Because it's vertically polarized. That's all there is to it. Deal with it. It's the best all-around portable vertical I have seen. In fact, let me take that another step. It's the best all-around portable antenna I have seen.
KJ6ER Poda Performer.
KJ6ER Poda Performer.
And it's a do-it-yourselfer with instructions available. All right. Now, this picture is something very similar to it and almost as good. And it's the Wolf River Take It Along. And it basically has a 102-inch whip on it, on a loading coil at the bottom, on a tripod. Still needs radials. This one, it's my belief, will perform better if you have a ground stake in the ground, right there where it's at, connect the radials onto the connection point on the tripod, and connect that to the ground rod. This one does not want elevated radials. Here's another picture of it in a guy's backyard.
You have to also change it every time you want to change bands.
It's the same thing. Now, if you look at this, you look all the way up the top there, you see the white ring. Here's that same coil on my pickup truck with 3 rings. I added rings. So what I did was, the way you tune this thing is you go to the band that you want to work on, and you slide this thing up and down until you get the most noise, and then you go into transmit or get an antenna analyzer. In fact, I built a little antenna analyzer kit that I could use just for this and keep it in the pickup truck. And if I have to change, I don't use it anymore because I bought extras of these little rings, and they each have an Anderson power pole on it. So that top ring is tuned for 20 meters. The middle one is tuned for 40 meters. The bottom one's tuned for 75 meters. So I just get out of the truck, unplug it, plug it into the next one, and away you go. All done. Now, because it's a low Q coil, it covers pretty much the entire band except for the 8075. It's real hard to find any antenna that'll cover all of that. But because it is low Q, I don't need any impedance matching. If I had a high Q coil in there, I'm going to need a little impedance matching. Here's another picture that I recommend for anyone that wants to do a portable antenna. If you look at the ball, just above the ball, you see that thing that looks like it's a hand screw. That's a quick disconnect. Breedlove Mounts produces both of those, and I strongly recommend them. It just makes it easier to put it up and take it down. So with twist of the wrist, I can loosen that up, take that antenna off of my pickup truck, and drive through the car wash. Trade-offs. It is a little easier to tune than the Poda Performer, at least within a limited number of bands, because all I have to do is move the wire on the loading coil. It requires radials, the same as the Poda Performer. Earth ground for radials, I believe, will improve efficiency, but more importantly, the distant far field probably perform a little better if you connect it directly to earth ground. It's pretty low cost, and it's available as a complete package or as parts. It's susceptible to urban noise like any vertical. It's less efficient than the Poda Performer due to the shorter fixed link whip. Poda Performer's got a 17-foot whip. Here we're talking about 102-inch. In fact, if you wanted to cover 10 meters, 102-inch whip's too long. You're gonna need something around the 93 inches length to be able to include 10 meters. It can be used with any whip between 48 and 108 inches, but there isn't any reason in the world why you couldn't use it with that same telescoping whip that the Poda Performer has, 17 foot. You do that, you're going to improve your efficiency at 80 and 75 meters, and 40 for that matter. It requires manual intervention to change bands. Walk outside, move the tap, go back in the house, and away you go. The Texas bug catcher on a tripod will work just like the Wolf River, but it gives you more options and better performance, all for more money. But it will perform better. Also, it's a lot uglier, so you can have some fun with it. How about taking a good screwdriver antenna and mounting it on a tripod? Now, some of the screwdrivers are good and some of them ain't so good. That ATS 120, whatever it is, it's a piece of crap. It's a useless. I mean, I've had people even brag about how well it works. The radiating element is just too short. It's not going to do anything well. But a Scorpion or a Tar Heel, or I don't know about the Diamond, but Diamond is selling a lot of it. They're not particularly expensive, probably made in Japan. And I think Doug, yours is a Harvest.
It's a High Sierra.
High Sierra.
Yeah, they don't make those anymore, though.
Okay. Well, Harvest is another brand that looks okay. I don't know if it is. There's one way to find out. But the cardinal rule is the longer that radiating element is, the better that antenna is likely to be. Now, there are some advantages to doing that. A lot of different ones to choose from. You can change bands remotely pretty easily. It will need ground radials, and an earth ground, I believe, will improve performance. Some versions are going to have a severely limited length radiating element. Good ones are going to have a high Q coil. But who cares if I have to retune it halfway across the band? Because I can do it remotely from my shack. Most of them can be configured with a capacity hat to electrically lengthen the antenna. Now, let's pretend for a moment that you want to go ahead and try putting an earth ground out where you stack your portable antenna. You see that plumbing box that you can buy at Home Depot or Lowe's? Dig a hole, put your ground rod in there, or put that down in the hole, put your ground rod all the way down in it, cover that, put the lid over it. You want to put your antenna out, pop the lid off, clip it onto your ground rod, bingo, you're done. How about a magnetic loop antenna? This is another excellent, as long as you're willing to take limited number of bands availability, and these work really well in the attic. And they're also pretty near impervious to noise, but they have some drawbacks. All right, works well in the attic. It's directional. And that can be a positive or a negative. Very high Q. It requires precise tuning as you move around the band. Now, what did I say about a high Q component? If I put 10 volts on a device with a Q of 200, I bet if I have a device with a Q of 2,000 or more. That's what you're going to end up with here. So no, that won't be on the coax. It'll just be on the device that it's dropped across. So no, you won't be stressing your coax. You can build this antenna yourself, and we've got a member that's successfully built one. But to tune it, you're going to need a capacitor that could take thousands of volts. That's tunable. And Randy McLean, when he did his, found an old Soviet military vacuum capacitor that he used, and he tunes it with a screwdriver motor. It is not susceptible to much noise. In fact, it's pretty near impervious to noise.
that the same one he took on his cruise?
Yes.
Okay.
It has limited band flexibility. It has limited power capability. The best ones I've seen would take about 345 watts SSB, a lot less CW or data. The one I showed you this picture on is for sale at DX Engineering for over $2,000.
You can't really skim through the bands listening.
No, you cannot. You change frequencies, you retune that puppy right then and there.
So everyone else there has to come to you, huh? Instead of you.
Well, if you know what if you're doing a Poda? They're going to come to you anyway. But you're going to point that thing the direction that you want to talk. You can do it yourself, but it's not simple. It's not simple unless you know how to do it. Randy McLean knows how to do it. I'm sure you could probably get him to help you with it. All right. One of our other members wanted me to mention this. Anybody like to hang their laundry?
Do HOAs let you hang laundry outdoors now?
Well, I'm just supposing we had just enough trees to hide this thing. What it basically amounts to is a fan dipole with each of the dipoles in a loop. The size is fairly small. A 20-meter version is about approximately 10 feet by 10 feet. So it isn't necessarily difficult to hide. It does like to be up over 20 feet off the ground, though. That is a negative. It is omnidirectional. It is multi-band because it's essentially a fan dipole. It's not very useful below 40 meters just because of size. That's not to say you couldn't do an 80-meter version of it and cover 80 meters through 10 meters or even 6. It's just that it's getting pretty big. It's a little less gain than a dipole. It's about 2 dB less gain than a dipole. The bands are likely to interact some like a fan dipole, which is basically what it is. So it may be a little hard to tune at first. Once you got it tuned, it's tuned. If you want to know more about this, talk to Doug Howard. I don't know anything more about this kind of antenna at all. In summary, for hidden or stealth antennas, expect lower performance than an ideal installation. Stealth antennas, though, still can provide adequate performance. And I might say that Performer, that was better than adequate performance, in my opinion.
I'd say if you can talk to another country, you're doing pretty well. I
would say you're doing extremely well. Now, I will tell you that the mobiles, the 2 mobile units that I've got, same type of radio, Wolf River coils, slightly different whips on them. I've talked all over North America with it from the car. On a mobile, you have a real weakness in that you got a lot of ground losses because the ground is capacitively coupled to the car. And so you got a lot of ground losses with it. If you'll connect your radio, if you've just got radials laid on the ground, that helps enormously. Then if you'll connect directly to the ground rod, which you can, by the way, also bond to the rest of your system, it's my opinion that the distant far field is going to improve some because of reduction in ground losses. But this is an important point. Unless you've got $1 million to throw away, minimum, on test equipment, there is absolutely no way to know for sure how your antenna is going to perform. Now, I like to tell people that I like to work on antique radios, and I guess I've got 4 different tube testers, and one of them's real good. And I can test tubes, and I test the tube, and it tests good, and I put it in the radio, and it don't work. Because the real test is, did it work in the radio? The real test on your antenna is, am I making contacts? That's really the cardinal test right there. If you're making contacts, you're in business.